question? Here's the worksheet, so let's, if you guys have a worksheet, take a look at that and answer any questions. Okay. So here is the worksheet. So you need to draw a bunch of ray diagrams. Basically, you use the rules that I gave you last time. And using the rules, you can see where the image is formed and what kind of image is formed. Whether it's real, virtual, magnified, diminished, upright, inverted. Okay, so you need to see that. So here is, oh, by the way, there is, we need to do a little bit of correction here. So I modified this picture, but I forgot to modify the numbers here. So we have a convex lens here, okay, and a concave mirror. So the focal length of the convex mirror is 2. Okay, so each box is 1 centimeter. So that's 2. Okay, so I should just write here each box or each division is 1 centimeter. And the focal length of this one is, so that's 1, that's 2, that's 3. So the focal length of this one is 3 centimeters, and the focal length of this one is 2 centimeters. And the object is 1, 2, 3, 4, 5 centimeters from the convex mirror. And the distance between the convex mirror, the convex lens and concave mirror is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 centimeters. Okay? So you need to draw the ray diagram and see where the image is formed. And you also need to see the image distance using the lens, thin lens equation. So you need to do this by drawing the ray diagram as well as by using the formula. So let's look at how to do that. First one is you need to see like how the image is formed by convex lens. So start with a ray that is parallel to the axis. So you need to draw the lines with a ruler. If you draw freehand, you won't get the right position for the image. So draw a straight line and hit the center of the lens. Okay, not the ray is bent at the center. I mean, it will bend here in the front part, but it will be more accurate in the ray diagram if we draw the ray bending to the center. So bend the ray to the center. Takes time to learn all new things. When you're using something for the first time, so this one goes, the first rule is if the ray is parallel, it goes to the focal point. So this dot is the focal point, so you need to pass the ray to the focal point. Okay, so that's the first rule. And the second rule is if the ray goes to the focal point and hits the lens, then it will be bent parallel to the principal axis. Okay, so the ray will be parallel. So draw it parallel. Okay. So that's the point where they intersect, and that's the real intersection. That means the image form would be real image. Okay? And you can draw a third one also. You don't need to draw the third one because you already know where the image is formed, but if you want, you can also draw a third ray to see if the rays meet at the same point. So pass it through the center of the lens, and it should go without any deviation or without any diffraction. So it should pass to the same intersection. Like that. And then you need to draw arrows to show where the ray is going through, I mean the direction of the rays. So that's the direction of the rays. Okay? And you need to draw image here. So the image is formed here, and this image would be inverted because it's under the axis, so it would be inverted. Okay? So this image is inverted. So that's the image. Now this image would be object for this meter. That means you need to draw a ray diagram for this meter. So the first one is again passing through the focal point. So this one. So when it goes to the focal point and hits the meter, it will be reflected back parallel to the axis. So this ray will be parallel to the axis. Okay. And the second rule is if it hits the meter parallel to the axis, let's say ray parallel to the axis and hitting the meter, then this would go through the focal point. So this will go through the focal point. Okay. And there is this intersection, real intersection here. And if you want, you can also draw the third one. Third one would hit the center of the meter. It's the center of the meter, and the reflected ray will have same angle as this angle of incidence. So it will have same angle. You see that's also passing through the same point. Okay. So you draw arrows to show the directions. That's incident rays, and these are the reflected rays. So there is refraction on this part and reflection on this part. So the rays intersect here, that means the image is formed at that point. And in this case, it would be upright for this meter because it's above the axis. So that's the image of the final image of the object. And again, it's upright because it's above the axis. Okay, so you can see here the image is formed at about 3 centimeters from the meter. So 1, 2, and 3, slightly less than 3 centimeters. We can consider that that's 3 centimeters. So final image distance, final image is about 3 centimeters, okay? About 3 centimeters from the meter. And it's upright, and it's about the same size as the object, and it's real because it's formed by the real intersection of the rays. Now you also need to do this by using the meter equation. So let's look at the meter equation. You guys have any question on the ray diagram?
So the bottom ray continues going across, right?
This one?
Yeah.
This ray is so that's originating from the object, so it goes straight. Yeah, you can assume that it's going straight. Yeah, that's fine. Because this ray hits the top and it just goes straight. I mean, there are like trillions of rays here, but we are considering only the rays that are relevant to formation of the image. Imagine that there are like trillions of rays going scattered everywhere. Okay, so let's look at now second method to see where the image is formed. So let's look at okay. So let's start with the convex lens. For convex lens, our focal length is 1 to 3 centimeters, and it's positive. Whenever you have converging meter or converging lens, for both converging meter and lens, focal length is positive. Object distance S, so how far it is from the lens? 1, 2, 3, 4, 5. So 5 centimeters. So you can find the image distance S prime by using the formula 1 over F is equal to 1 over S plus 1 over S prime. So 1 over S prime is 1 over F minus 1 over S. 1 over F is 3 centimeters minus 1 over S. That's 1 over F. 1 over S is 1 over 5 centimeters. You can use calculator, but I will do this math here. So the least common denominator here would be 15. So to get 15, you need to multiply 3 by 5. To get 15, you need to multiply 5 by 3. So that's 2 over 15. So that gives me S prime is 7.5 centimeters. By the way, last time, if you watched the videos or if you were in the class last time, I did wrong conversion between millimeter and centimeter, but I corrected that on the PowerPoint. So last time I used 1 millimeter is equal to 10 to negative 2. Actual conversion should be 10 to minus 1. Okay, so that's the image distance for convex lens. Now, this will be the object distance for the concave meter. Now use the same equation. 1 over s prime is equal to 1 over f minus 1 over s. 1 over s prime. The focal length of the meter is 2 centimeters. So this dot is 2 centimeters from the center of the meter. 2 centimeters minus. Now this would be the object distance again. 7.5. The least common denominator for this one will be 15. So that's 7.5 minus 2. That gives me 5.5 over 15. And then to get S, you need to flip on both sides. So flipping on both sides, I get 15 over 5.5, which is the it's a little bit less than 3, right? What do you get? 2.7. 2.7 something centimeters. Okay. So in our previous calculation, in the ray diagram, we got S to be about, we didn't know exactly how much the distance was, but here we got the exact number. So previously we got about 3 centimeters. So here it says it's 2.7 centimeters, exact number. So that's how you do that. Okay, let's look at another one. So we did this number 3 last time. So let me show you how you do that once again if you were not here last time. So the far point of nearsighted person is 49 centimeters from his eyes. Find the refractive power of eyeglass needed to correct this problem. Okay, assuming the glasses are 1.6 centimeters from the eyes. So let's first see the problem here. So you have eye. Has lens. Okay. Now usually in normal circumstance the far point is at infinity. You can look at objects at infinity very clearly. You have normal eye vision. But for nearsighted person the far point is shifted to some distance closer than infinity. Okay, so in this case, the near point is at 49 centimeters, so it's here. So that's the near point. Instead of at infinity now, it's at 49 centimeters. Okay. Now, in order to correct this, you need to wear a diverging lens or concave lens, and the lens is 1.6 centimeters from the eye. Now, in order to see the object at infinity clearly, let's say you have an object far away here, in order to see that clearly, this lens needs to form the image at this near point, because you can see only up to that point. Beyond that, it's blurry. Okay? So you need to form the image of this object at that point. That means image distance would be that. So this distance would be the image distance, S prime, because the function of this diverging lens is to form image of this object at that point. So our image distance would be S prime. What is S prime here? So near point is distance from that point to your eye, so which is 49 centimeters. And the distance between the lens and the eye is 1.6. That means what is S prime? This whole thing is 49. That is 1.6. What is this distance? S prime. You have 49. You have 1.6. What is this distance? Hmm? 50.6. Okay, so 47. Yeah. So you are subtracting this 1.6 from whole distance, right? So 49 minus 1.6, which is 47.4 centimeters. And the object distance, it's at infinity. It's far away from your eye, because you want to see the object at infinity. Now we need to find focal length first to find the refractive power, because we know refractive power is 1 over f. So to find that, we first need to find 1 over f. 1 over f is given by this formula, 1 over s plus 1 over s prime. So 1 over s is infinity, 1 over infinity plus. And one more thing you need to be very careful here. That is, diverging lens always forms virtual image. Okay, so this forms virtual image. How do you know it's virtual? Because it's upright. Okay, and it's on this same side. If it forms the image on this side, okay, like this with the convex lens, if the image is formed on this side and if it is inverted, then it's real. But if it is upright and on this side, then it's virtual. So this forms the virtual image, and the sign convention tells us that for virtual image distance is negative. So we need to put minus sign there. Okay, so it's not here. But we need to say this should be negative because it's a virtual image. So we need to put minus sign here. Minus 47.4. So that means 1 over infinity is 0, 1 over large number is 0. So then we need to flip on both sides to get f. That gives me minus 47.4 centimeters. That's the focal length. But I need to find the refractive power. Refractive power is defined as reciprocal of focal length. And if you remember, to find the refractive power in the unit of diopter, the unit of refractive power is diopter. To get that, you need to express f in meters. Okay? So this is in centimeters, you need to express that in meters. So 47.4 times 10 to negative 2 meters. So that would be 1 over negative 47.4 times 10 to minus 2 meters. And then you do the calculation, that will give you R. So minus is that 2 minus 2 or 2 point something? 2.1. Can you do the calculation, please?
Negative 2.1.
2.1. 2.1 diopter. That's the refractive power, okay, that you need to wear to correct the vision disorder. Any question on this?
What was the S prime negative one?
Okay, sorry?
Why was the S prime negative?
Why is this prime negative? Okay, that's a good question. The reason is, if the image is virtual, we use the image distance to be negative. And the image formed here is virtual because it's formed on the same side of the object. Object is on this side and the image is also on that same side. If that's the case, usually you see the virtual image. Also, that's upright. The image formed is upright. That's virtual. So, for virtual object, for virtual image, the image distance is always negative. Does that make sense? Good. Okay. Let's look at another problem. We should be able to do number 5, we did last time. 4 also, it's pretty straightforward if you use the formula. So 6 would be a little bit tricky. So let's look at number 6. So this is a little bit tricky. It involves some logic here. Okay. So we have a microscope that has eyepiece and an objective lenses that have 13x and 58x magnifications, and they are 20 centimeters apart. So let's see the picture. We have this objective. So the lens. The lens that is closer to the object is called objective. So this is objective. Its focal length is for objective. Focal length is not given, so we use FO for focal length of objective. Its magnification is given, MO is 13x. And we have eyepiece, the lens that is closer to the eye is called eyepiece. So this is FO, and we have FE, eyepiece. FE, focal point for eyepiece. So the question tells us that, and this is always true, that in microscope the object is placed close to this focal point of the objective. Okay, so we usually place the object here, small tiny objects here. And the question tells us that we want to form the final image of this object at this point. Okay, that's what it says. So for part C, where the object must be for normal relaxed eye to see it in focus. Okay, so that's the final image. So we can treat the lenses independently here. So for objective, that's that, and then for eyepiece, focal length is FE, not given. Magnification is ME, which is, sorry, so for objective it's 50th times, okay? So objective is 50th times magnification. And eyepiece is 13 times magnification. Okay? That's what we have. And then other information we have is these lenses are 20 centimeters apart. That's all we have. That's information. Let's look at the first one. So what's the total magnification? So the total magnification is multiplication of the individual magnifications. So total magnification is ME times MO. So you multiply 13 and 58, that gives you the total magnification. What's the focal length of each lens? That's pretty straightforward. If you know the formula, that's pretty straightforward. So we know for objective, the magnification is defined as, the objective acts as a magnifying glass. Okay? And for magnifying glass, the magnification is 25 centimeter over the focal length of the objective. It's not object. Eyepiece acts as the eyepiece. This side acts as the magnifying glass because it forms the virtual image. Okay. So for objective, this is the tube. That's the objective lens on one side of the tube, and the image is usually formed here on the edge of the tube. So that means so objective. So the magnification is defined as image distance over object distance. In this case, image distance is L. That's the distance between image and the lens. And object distance is, it's near the focal length, so we use FO. Okay, so that's the magnification of objective. And to find FO, we can reorient that. So minus L over M naught. So L is the tube length. If you guys remember, if you were in the last class or if you saw the video, the standard tube length is, you guys remember what that is?
160.
Yeah, 160 millimeter. In centimeters, it would be 16, right?
Yeah.
The 16 centimeters. So 16 centimeters is the standard tube length, even if it is not given. You need to know that. Or if it is exam question, it will be provided in the exam. And MO is the magnification of objective, which is 58. So that gives us. Can you guys do the math? Sorry?
Why is it L20? Because that's how far the lenses are from each other.
Why isn't L20?
You wrote it up at the top.
Yeah, you said only use 160 if it's not given.
Oh, so you guys are saying that I should use. Go up. So I should use 20 for the tube length. That's what you're saying.
Yeah.
Okay, so the lenses are not fitted within the tube. So you have one microscope has multiple tubes. Okay, so you'll have let's see. you have a tube here. So let's say your image is formed here. Then you'll have a tube here. This tube would be about 16 centimeters, and you'll have another tube here. So this is the eyepiece tube, and this is objective tube. So that means we cannot use 20 centimeters. 20 centimeters is from one edge of the tube to the other edge of the other tube. But we need the image distance here. Image distance is this distance, which is the distance between this lens and where the image is formed. And the image is formed usually on the edge of the first tube. Does that make sense? So 20 centimeters again is the distance between the two lenses, not the object, not the image distance. Any other question? So if you look at microscope, I don't have the picture with me here, so let's find a microscope. Doesn't want to show me the picture. I mean, you can see from here. You have here this tube and that tube. Okay, so the image of the first lens is formed at that point, okay? Usually. So that's the eyepiece. Sorry, we are talking about this one. So this is the objective. So image is formed here, and then that image becomes the object for that one. Okay, so this distance would be L. But we are talking about this distance, which is the image distance. And the image distance would be the length of that tube, which is 160 millimeters.
So in these calculations, L is always 160?
Yes. Okay, so let's find F naught. Again, the magnification for objective is minus L over F naught. That's the formula. So we need to get F naught. F naught would be L over M naught. So L is the tube length, which is 16 centimeters, and magnification is 58. Is that 58? 58. And very important thing here is this is a convex lens, and it forms when the object is beyond the focal point. If it is within the focal point, it forms the virtual image. But if it is beyond the focal point, it forms the real image. Okay? So it forms a real image on this side. So it would be inverted. That means this magnification needs to be negative. So that's what you need to use. That's where you need to use the sign convention. So here it would be a virtual image, inverted image. So for inverted image, you need negative magnification. So let's do that calculation. 16 over 50. Let's see what you get.
0.276.
Hmm?
0.276.
0.276. Okay, that's the magnification. That's the focal length. Okay, centimeters. Now we need to look at the other one. So for eyepiece, let's look at eyepiece. So for eyepiece, so ME is defined as 25 centimeter. We used this formula last time. So over FE. Okay, we're going to find FE. FE is 25 centimeters over ME. 25 centimeter. ME is 13, I think. So that gives me it's a little bit less than 2, 1.9.
Yeah.
1.9 centimeter. Okay. So that's part B. Now for part C, let's look at part C. Any question for part A and B? It's pretty straightforward. First one is just find the total magnification, which is the multiplication of two magnifications. And then for the second part, you just use the formula for magnification, individual magnifications.
Where's the 25? So,
This is the formula.
like the 25 is.
It's just
It's
constant,
already in
constant number. And I can explain like how it is there. I would recommend you to watch the last video because I explained that in the last video how we get that. So that's the near point of our eye. Okay, object is usually near the near point of our eye. That's why it's there. Okay, so let's look at the last one, number part 3. So where the object must be for the normal relaxed eye to see. So let's look at this part. Okay, so let's think about this. So we have that lens, and our final image is at the focal length of this one. So at F, this is objective, this is eyepiece, so this is F O. So then what would be the S prime? S prime is distance between the image and the lens. So we want to find this first, to find the object distance. So what's S prime? So this is 20 centimeters. And this is, we just found that. Can you guys tell me what that number is? I don't remember. What's that? 0.276. So that's 0.276, and the whole distance is 20 centimeters. Then what is this distance? 20 centimeter minus 0.276, right? So that gives me what? 19.72 centimeters. And this is the virtual image. Okay. So you need to see the diagram. You need to draw the diagram before this problem. It will show that this is the virtual image formed by that. So your object will be somewhere here. Sorry, it will be somewhere here, and you have this upright image here. So this is the virtual image due to the producing the raised background. So you need to put minus sign here, okay, because this is virtual. Okay, and then focal length is known. So focal length is F. We are talking about eyepiece. So E is what's that? Is that 9? 2. 1.9 centimeter. And this is positive because it's a converging lens. For converging lens, it's positive. Okay, so we can find 1 over S by using this formula. So 1 over F is equal to 1 over S plus 1 over S prime. Okay, so 1 over S would be 1 over F. E minus 1 over S prime. Okay. 1 over F is 1.9. Minus and minus would be plus 1.19.72. Okay, you do the math. So S would be something. Okay. So that's the object distance. So this distance. Now this object is the image of this one. Okay? So this object comes from the image formed by this lens. It's the image of objective. That means for objective, our S would be, S prime would be whatever you get from here. If you guys can give me a number, I can put it here. So that would be S prime. And then we know FO, focal length of objective, which is 0.27 something. With that we can find S. Okay? Can you guys give me a number here? I can then show you how to do that. So just give me a number, what you get for S here.
0.58.
Huh?
0.58.
5 centimeter. Okay. Assuming that's correct, so this will be 0.58. Okay? Because again, this now is the image distance for the objective, because this is the image formed by the objective. And then focal length is that. So now, last step. So we need to use this formula: 1 over S, 1 over F is equal to 1 over S plus 1 over S prime, and we want to find S. So 1 over S would be 1 over F minus 1 over S prime. So 1 over F here is, we are talking about the objective here. 0.27 minus 1 over S prime. This would be positive because it's a real image, it's inverted. So S prime is 0.58. And you do the math here, okay? So that will give you S. Okay, someone, if you can do the math, I can put the number here. Everyone can check the number. So let's find S from here. Anyone has number for this? No? I think you guys can do that, okay? So I think that's all for today. We are out of time. We'll start new chapter from next time. New chapter is completely different one, okay? So it's not related to anything that we are doing so far. If anyone has number, I can write the number here. Sorry, 1.85. 1.85. You guys can check the answer and see.